In August 2024, Tory Bruno, who was then the CEO of United Launch Alliance and thus the head of the only other notable American rocket manufacturer besides SpaceX, had a remarkable reaction to the first official photo of the Raptor 3. He posted a comment suggesting that SpaceX had presented a half-assembled engine. He noticed that it was missing all the piping, the flanges, the external wiring that he would expect from a finished rocket engine. Bruno was wrong. What he saw was a complete Raptor 3. The seemingly missing components were integrated or optimized away. What we have here is not an iterative update to the previous model. It is an engine that forces the established industry to question its own standards. Today, we are doing what we haven't done before. We are going as deep as we can. How exactly does a Raptor 3 work? What pressures are present where? What temperatures? What materials? How is the flow? What was really simplified? And why is the whole industry talking about this engine being a generational leap? My name is Serwan and this is Mars Chronican. Before we take a look inside the Raptor 3, we need to clarify a fundamental architectural question. Because a rocket engine is not just a combustion chamber with a nozzle, it is a highly complex thermodynamic system that draws fuel from tanks, sometimes brings it to extremely high pressure, burns it in a controlled reaction, and expels the resulting gases at high speed out the back. Exactly how this happens depends on the so-called engine cycle. There are different families of these cycles. There are open cycles like the gas generator or the tap-off, or closed cycles like staged combustion or expander. Open means in this case that parts of the propellants do not pass through the main combustion chamber, while in closed cycles all the propellants go through the main combustion chamber. At the very top of the efficiency hierarchy is the cycle variant of staged combustion called full-flow staged combustion. In German we say Vollstromgestufte Verbrennung. Cumbersome but precise. The Raptor uses this cycle. What makes full-flow stage combustion so special is best explained by a single number. In the entire history of spaceflight, only 3 engines have ever been developed that were actually able to fire on a test stand using this cycle. The first was the Soviet RD-270 in the 1960s. It never flew and the program was cancelled. The second was the integrated powerhead demonstrator by Aerojet Rocketdyne, a joint project with NASA in the early 2000s SE. This one never flew either. The third is the Raptor. It is the only full-flow stage combustion engine that has ever flown operationally. And with Raptor 3, SpaceX is perfecting a cycle that the greatest engine engineers in the world have failed at for 60 years. Meanwhile, there are 4 more of this kind in development. The Zenith at Stoke Space, the Aerowave from Ursa Major, the BF-BF-20 from Landspace, and the Mjolnir from New Frontier Aerospace. Let's now understand why full-flow stage combustion, especially in the Raptor version, is so awesome. In a classic rocket engine, let's say the RD-180, which still powers the Atlas V to this day, there is a single pre-burner. This pre-burner is basically a small combustion chamber that burns part of the propellant and uses the resulting hot gas to drive a turbine. This turbine in turn drives the propellant pumps that force the actual propellant into the main combustion chamber. And what happens there is absurd. For one thing, the RD-180 is also a staged combustion engine. So, they want to burn the exhaust gases from the turbine further in the main combustion chamber. For that, even after leaving the turbine, they need to have a high enough pressure so they can be pushed into the main combustion chamber. In the main combustion chamber of the RD-180, there is a pressure of 267 bar. Friction losses and the expansion. Taking into account the expansion over the turbine, the mixture initially needs to have more than twice as much pressure. But it gets even more impressive. When the Americans were able to examine the RD-180 for the first time, which was after the fall of the Soviet Union, they were stunned. The Russians had managed to achieve lean pre-burning. Anyone who knows about engines is familiar with lean combustion. In this process, the mixture of air and fuel contains so much air that there is more oxygen present than can be burned with the amount of fuel. That doesn't sound particularly special. The subtle difference here is that air consists of 80% nitrogen, and in a lean combustion, this nitrogen keeps the oxygen from causing a lot of trouble. But in rocket engines, pure oxygen is often used, and oxygen mixed with nitrogen at room temperature is already nasty. It reacts very readily with everything around us. Rust, for example, is a result of that. But in the pre-burner, temperatures of around 600 degrees Celsius prevail, and only a small part of the oxygen is burned with a kind of kerosene in the case of the RD-180. Unbound hot oxygen is eager. But really eager, it wants to form a close bond with just about everything and everyone around it. For example, steel. Normal stainless steel handles warm air well and doesn't rust. But at 600 degrees Celsius, even that becomes weak. Here, the Russians found an alloy that still doesn't give in. An alloy that the Americans had been searching for a long time, but hadn't found until the fall of the Soviet Union. Now, of course, you might ask why the Russians didn't just use the kerosene fuel flow to run the pre-burner. After all, a rich combustion would bind all the oxygen, and hot kerosene, when there's no oxygen left, has no interest in reacting with other substances. The problem with kerosene, however, is that it doesn't burn cleanly and could therefore clog the turbine with soot particles. Now there's hydrogen, or, as in the case of Raptor, methane, which burns cleanly as a rich mixture. Great. So why all the hassle with the full flow? It means that both substances, in our case the oxidizer, which is oxygen, and the fuel, which is methane, are pre-burned. If you're a bit crazy and think that 267 bar in the main combustion chamber isn't enough, then with pre-burning using only oxygen or only methane, you quickly reach temperature limits. Even if the alloy might withstand hot oxygen, steel in general starts to lose stability above 600 degrees Celsius and already suffers too much from the heat alone. Full flow stage combustion solves exactly this problem in an elegant way. Instead of one pre-burner, there are now two. One runs methane-rich and drives the methane turbopump. The other runs oxygen-rich and drives the oxygen turbopump. Both operate at significantly lower temperatures than a single pre-burner would have to, because each of them only has to do part of the pumping work. That dramatically extends the lifespan of the turbines. And that means something very specific for the combustion. All the propellant, that is methane and oxygen, has gone through the pre-burner step before it enters the main combustion chamber. Both propellant streams are then gaseous. Not liquid, gaseous. And they have already absorbed energy. That's the central idea. When liquid methane meets liquid oxygen, it first has to be vaporized, then mixed, then ignited. When gaseous methane meets gaseous oxygen, they practically mix instantly and burn even cleaner. This way, all the energy is released in the combustion chamber and can be used most efficiently here. Well, if you didn't have to work with film cooling, but more on that later. That's what the Raptor 3 does. If you're as excited about this as I am, then hit the hype button if you have it. If not, a like, subscription, or a comment also helps the channel a lot. Today, we're going into technical details like we've never done before. Whoever sticks around will know more about full-flow stage combustion than 90% of all spaceflight influencers in the German-speaking world. Promise. Thank you, and let's continue. Let's now follow the propellant through the engine. That's actually the best way to understand what's happening. Everything starts in the rocket's tanks. The booster contains 2,700 tons of liquid oxygen at under minus 183 degrees Celsius. and 700 tons of liquid methane at below minus 162 degrees Celsius. Both are cryogenic, meaning below their boiling points, which makes them denser and increases the mass flow rates. Each of the 33 booster engines draws its share from these tanks using 2 turbopumps, 1 LOX pump and 1 methane pump. The ratio is about 3.6 to 1 in favor of oxygen. Some methane is deliberately wasted because the chemistry increases the specific impulse by a few percent. The pumps are damn small for what they do. A Raptor turbo pump spins at over 45,000 revolutions per minute, pushing around 180 kilograms of methane and about 660 kilograms of oxygen per second through the system. So, in 2 seconds, the weight of a Passat station wagon goes through a Raptor. The turbopumps generate a pressure of roughly 800 bar. Everything flows downstream and runs at lower pressure. By design, otherwise it would flow in the other direction. And keep in mind, in the main combustion chamber, Raptor 3 still has about 350 bar. Now comes the first trick. Before the main flow of propellant goes into the combustion chamber, it is routed through the 2 preburners. The LOX preburner gets almost all the oxygen plus a small amount of methane. The methane preburner gets almost all the methane plus a small amount of oxygen. Both ignite, one with oxygen-rich combustion, the other with methane-rich combustion. The temperatures are below the critical thresholds that would destroy the turbine blade material because the mixture ratio is far from stoichiometric. The hot gases from these 2 preburners then drive the turbines, which in turn drive the pumps. That is the self-sustaining system. The pumps push propellant through the preburners. The preburners provide energy for the pumps. But now, here's the crucial point. These hot gases are not vented, they move on. Both streams enter the main combustion chamber. There, they mix, gas to gas, and complete the final stage of combustion. That's exactly what staged combustion is. Combustion in stages, and because nothing escapes unused here, the engine achieves its extreme efficiency. And something else happens here that shows the full elegance of this system. While the fuel is being sucked out of the tanks, a problem arises inside the tanks themselves. They would collapse. Imagine you're sucking from a plastic bottle without letting any air in. It contracts. With a rocket containing 3,400 tons of fuel in thin-walled steel tanks, that would be catastrophic. So the pressure in the tanks has to be actively maintained, while they're being emptied at an insane speed. The classic solution for this is helium. So you take externally stored helium from high-pressure bottles and let it flow into the tanks while the fuel is draining. It works. But it has 3 problems. Helium is expensive, in short supply worldwide, and helium tanks add weight that you'd rather use for your payload. But what does that have to do with the Raptors? SpaceX has found an extremely elegant solution to this problem, and that's autogenous pressurization. Here's how it works. Before the methane and oxygen enter the preburners, a small portion of them is diverted. This portion is vaporized using the residual heat from the engine. That happens anyway through regenerative cooling. The resulting gases, gaseous methane and gaseous oxygen, are then routed back into their respective tanks. They fill the space left by the pumped-out propellant and thus keep the pressure constant. But that's not without its challenges. Because in the tanks, such hot gas comes into contact with cryogenic liquid. So over time, the liquid warms up and the gas cools down. So the pressure decreases. If the liquid sloshes, there can be a sudden release of pressure. All of this can be solved, but it must be taken into account and finely controlled. So the engine not only supplies itself with energy, but also keeps the tanks it draws its propellant from pressurized. A closed cycle, no external helium, no additional system. Just a small diversion from the propellant flow that elegantly solves the problem. It's the same principle again. Leave out what can be integrated. As you can imagine, it's also an enormous achievement to generate the right amount of gas and let it flow into the tanks, because you want to avoid too much or too little pressure. All these parameters have to be exactly balanced. Just thinking about it already makes me feel overworked. There is a pressure of 350 bar in the main combustion chamber. That's about 350 times as much as the atmospheric pressure at sea level. For comparison, the famous F1 engine of the Saturn V, which brought Apollo to the moon, had only 70 bar of chamber pressure. The Space Shuttle main engine, for a long time the most technologically impressive engine of its time, had 207 bar. Raptor 2 reached 300 bar. Raptor 3 pushes the limit to 350 bar. That's physically close to the limit of what's even possible with current materials. The temperature in the combustion chamber, about 3,250 degrees Celsius, that's hotter than the melting point of most metals. Steel melts at 1,500 tungsten, the most heat-resistant metal of all, melts at 3,422. That stuff is used in light bulbs, for example. Before we take a look at how the engine survives these temperatures, we first need to briefly deal with perhaps the most difficult phase of a Raptor engine: the startup. Because the engine in steady-state operation is a stabilized thermodynamic system. But how does it get there? And in what order? The engine startup is a dance that happens on a sub-second timescale where everything has to follow a very specific choreography. If even a single component does its job a tenth of a second too early or too late, the engine goes into a state that the industry calls RUD. Rapid Unscheduled Disassembly. Rapid Unplanned Disassembly. In other words, it explodes. The sequence has two phases and both are tricky. The first is preparation. The fuel in the tanks is cryogenic, we already know that. If it comes into contact with warm pumps or pipes, it instantly vaporizes and produces vapor bubbles that would destroy turbopumps in seconds. That's why SpaceX actively cools the engine minutes before launch by letting small amounts of fuel flow through the system. That's the controlled dripping you see under the engines during Starship launches. It's not a leak, it's engine chill. At the same time, the turbopumps have to spin up before the actual ignition, otherwise they wouldn't let the incoming fuel flow through. For this, they are briefly spun up with high-pressure helium or cold propellant gases supplied from the ground at launch and for re-entry and landing from their own core PV tanks on board, which are carbon fiber-wrapped high-pressure bottles with helium. The second phase is the actual ignition. First, the pre-burners are ignited by an electric spark igniter. The hot gases flow through the turbines and the turbines drive the pumps. The external drive is switched off. The system switches to self-sustaining operation. Fractions of a second later, the gaseous preburner exhausts meet in the main combustion chamber and ignite. Full thrust. What's fascinating isn't that this works. What's fascinating is that it has to work with 33 engines at the same time. If even one of them doesn't complete its sequence properly, it drops out of the cluster and the booster launches with 32 engines. 3 failures get uncomfortable. 10 mean no launch. The parallel startup is by far the most difficult moment of the entire flight. And at the same time, it's the economic justification for 33 engines. Redundancy. SpaceX has never publicly documented the exact second-by-second choreography. What I just described is the reconstructed sequence based on public statements, test footage, and generally known full-flow staged combustion principles. Now to the question of how the engine survives these incredible temperatures and pressures. The answer? Regenerative and film cooling. The walls of the combustion chamber and the nozzle are not solid. They are traversed by fine channels that run parallel to the outer wall. Before the methane is pumped into the pre-burners, it first flows through these channels. The cold methane, still close to minus 160 degrees, absorbs heat from the combustion chamber walls as it flows through. It actively cools the walls while itself transitioning from a liquid to a gaseous state. That's totally elegant. You take the heat that you would otherwise have to get rid of and put it back into the fuel. A double benefit. The combustion chamber doesn't overheat, and the methane arrives preheated in the preburner, which further increases combustion efficiency. With the Raptor 3, this mechanism has been dramatically expanded. While Raptor 1 and 2 still had many external components that needed a separate heat shield, with Raptor 3 the former external lines were moved inside the main structure and also cool other components of the engine. They are now directly in the path of regenerative cooling. The heat shield has thus become unnecessary. Completely. Not reduced, not simplified, but left out entirely. According to SpaceX, this single step alone saves about 1 ton of mass per engine when you include the associated vehicle components. With a total of 39 engines per stack, 33 for the booster and 6 for the ship, that's a mass saving of 39 tons. That's 39 tons that can now be used for payload or fuel instead of heat shields. That's more than the entire James Webb Space Telescope weighed when it launched to Lagrange Point 2. However, this cooling alone isn't sufficient for the throat of the combustion chamber, where it transitions into the nozzle. Here, methane is also injected directly into the gas stream through tiny holes to protect the wall from the rushing heat. Strictly speaking, this means Raptor is no longer a fully closed cycle because the cooling methane exits unburned. But the gain in pressure more than makes up for the loss in efficiency. There is a way of thinking that all truly groundbreaking engineering products have in common, leaving out anything that doesn't add value. With the Raptor, 300s of external components were eliminated because they could be integrated. The combustion chamber cools itself, the methane is preheated, the heat shield was completely eliminated. Nothing is left that doesn't have to be there. This exact philosophy has also been adopted by the sponsor of this video. Nuki, an Austrian company from Graz, has been building the smart lock since 2015, which applies exactly this idea to door locks. You don't need to drill anything, you don't need to replace anything, and you don't need a locksmith. The Nuki smart lock is simply mounted on your existing door lock from the inside. In under 5 minutes with the Smart Lock Pro, in under 15 minutes with the Smart Lock Ultra. No drilling, no screws, no violation of your rental agreement. What you have afterwards is your door, but smarter. It opens automatically when you approach, thanks to auto unlock. You control it with your smartphone, smartwatch, fingerprint, or a 6-digit code. You can grant access to family or workers via the app. For a limited time, revocable at any time. And if someone asks you whether it's secure, Nuki is developed in Austria, produced in Europe, and therefore subject to the strictest data protection standards in the world. Made in Europe is to be understood here as a promise of quality. If you want to upgrade your door lock without changing the entire setup of your apartment, you'll find the link to Nuki in the description below. Or simply through this QR code here. With the code MASCHRONIKEN, you get 15 off the Smart Lock Pro and the Smart Lock Ultra. And now back to the Raptor. So where were we? At the now unnecessary heat shield. But that's not the only radical step with the Raptor 3. Let's look at manufacturing. Raptor 1 was built in the classic style. Many individual components, welds, flanges, screw connections, hundreds of parts that each had to be manufactured, inspected, and assembled. That was expensive and slow. A Raptor 1 cost around $2 million each. With a booster with 33 engines, that's $66 million, plus another 6 engines for the ship, so another $12 million. A total of $78 million per stack. Just for the engines. With Raptor 2, SpaceX fundamentally redesigned the engine. Welds replaced many flanges. Sensors were consolidated. The turbopump was newly designed. That brought the unit price down to around $1 million. Half of it. But that was just the preparation. With Raptor 3, SpaceX has taken manufacturing to another level. Here, 3D printing is used on a large scale. Not in the way we know it from a hobby printer at home, but rather laser powder bed fusion and binder jetting. So, industrial metal printing processes that produce entire components in a single piece, which used to be assembled from dozens of individual parts. The turbopump housing, for example, is a single monolithically printed component in the Raptor 3 no-weld seams, no potential leak points. The injector plate, which is the component that injects the fuel into the combustion chamber in a controlled way, is also a single printed piece with built-in cooling channels in the Raptor 3. Overall, the Raptor 3 has about 30 fewer components than the Raptor 2. And thanks to the simplification, the price drops again to around $250,000 per engine. For context, the Space Shuttle main engine, which is also used by the SLS, the RS-25 costs about $100 million each. What a waste of money. When it comes to materials, Raptor 3 uses high-performance alloys. The combustion chamber and nozzle walls are made of copper and Inconel, a nickel-based superalloy that remains highly corrosion-resistant even at high temperatures. Inconel also melts at around 1,300 degrees Celsius, but this is where regenerative cooling comes into play and prevents it from melting. Sounds absurd? However, you can observe a similar phenomenon if you fill a plastic bag with water and hold a lighter to it. Actually, the plastic should melt immediately, but the water cools so well that the plastic bag withstands the heat. For the components that come into contact with pure hot oxygen, SpaceX has developed its own alloy, SX500. It was specifically developed for oxygen-rich combustion at extremely high pressure and can withstand oxygen gas at up to 810 bar. This is an in-house development that is not used in any other engine in the world. What really shocked the industry about the Raptor 3 is the combination of all these factors. Building an engine that delivers more thrust than its predecessors is routine. Building an engine that is lighter is also routine. Building an engine that is cheaper is a dream. But all three at the same time? That was considered impossible in the industry. Raptor 1 weighed 2,080 kilograms and delivered 185 tons of thrust. Raptor 2 weighed 1,630 kilograms and delivered 230 tons. Raptor 3 weighs 1,525 kilograms and delivers 280 tons. With each step lighter, stronger, cheaper, the industry has a word for it. Positive feedback loop. When everything gets better at the same time, you can scale everything at the same time too. The specific impulse, meaning efficiency in the strict sense, is 334 seconds at sea level and 350 seconds in vacuum for Raptor 3. For comparison, the highly advanced RS-25 reaches around 366 seconds at sea level. However, in vacuum, it achieves 452 seconds. However, for that you need hydrogen as fuel, which brings a whole range of other problems with it. By the way, SpaceX's first ideas for the Raptor were also hydrogen-based. However, they decided against it for pragmatic reasons. But the details about that are a bit too much for this video. The vacuum variant of the Raptor 3, which is equipped with a large nozzle for vacuum operation, is expected to achieve 380 seconds of ISP in the long term. But that still needs a bit more work. Currently, it's more like just under 370 seconds. And Elon Musk has publicly said that Raptor 3 is not the end of the line yet. Future iterations are expected to reach 300 tons of thrust and a thrust-to-mass ratio of over 200. That would be the highest value any rocket engine has ever had. Let's look at the test cadence because that's at least as impressive as the technical data. By April 2026, SpaceX has produced over 600 Raptor engines in total. Over the past 2 years, more than 40,000 seconds of cumulative burn time have been logged with Raptor 3 configurations on the test stand. That's over 11 hours of pure engine ignition, spread across hundreds of individual tests. With a typical Raptor burn duration of a few seconds per test, that means more than 1,000 individual ignitions on horizontal and vertical test stands in McGregor, Texas. Recently, however, longer tests have also been recorded more frequently. And we get to see everything thanks to the cameras that NASA Spaceflight has set up on site. It's incredible, the times we live in. By the way, McGregor is not a random location. It's been the SpaceX engine facility since 2003. The first Merlin was tested here. Today, every single Raptor is fired up here before it goes to Boca Chica or Florida. Over the years, the facility has built dozens of test stands. All of them can be operated in parallel. On some days, several Raptor engines fire simultaneously in different configurations and profiles. The area around McGregor looks like an industrial facility. Residents have gotten used to the distinctive sound produced by an igniting Raptor. The production rate is now so high that Raptor engines are literally being built for inventory. In 2022, it was reported that SpaceX was producing 1 Raptor per day. Today, the rate is probably much higher since the Raptor 3 was developed for production. We might be talking about several engines per day here. With 33 engines per booster and 6 per ship, so 39 per full stack, SpaceX could theoretically produce a complete set of engines every 4 weeks or even faster. That doesn't mean SpaceX needs 24 hours to build an engine. Rather, it means that 1 engine leaves the production line per day. What this means economically can be summed up in a single number. At $250,000 per engine, the entire propulsion section of a full stack costs less than $10 million. Falcon 9 currently delivers payload for around $3,000 per kilogram to low Earth orbit. Ariane 6 for $5,500, New Glenn for $1,700. If Starship V3 comes in as planned at under $50 million per launch and lifts at least 100 tons reusable to orbit, we're looking at around $500 per kilogram. 6 times cheaper than Falcon, 9 more than 10 times cheaper than Ariane 6, and still a factor of 3 compared to New Glenn. That doesn't change the market. It changes what can even be imagined as a market. For the established space industry, that's a structural problem. The BE-4, which powers both Vulcan and New Glenn, is oxygen-rich staged combustion with only 1 preburner. The performance gap to the Raptor 3 is real and can't be closed with software. Tory Bruno has publicly hinted that the Vulcan may need to be redesigned to remain competitive. For NASA, on the other hand, the entire Artemis program depends on the Raptor 3. The HLS lunar variant needs orbital refueling. Orbital refueling requires tanker vehicles. Tanker vehicles need massive thrust reserves. Massive thrust reserves need Raptor 3. Without Raptor 3, a manned moon return won't happen while it's still politically sellable. And furthest in the future, but most importantly, Raptor 3 turns Mars from a vision into an engineering question. SpaceX has postponed the Mars missions to February 2026. That was a political decision, not a technical issue. What is still missing right now to make it a reality is orbital refueling, a fully reusable ship, a lunar base as an intermediate station, and above all, more flight experience with the Raptor 3 itself. Hopefully we'll start gaining that experience on May 20th. There's a moment in last week's SpaceX video where Jacob McKenzie, the vice president for Raptor, is standing in front of a forest of finished engines. He says, loosely translated, "Something is only impossible if it breaks the laws of physics." We are not breaking any laws of physics. We're just trying to use them as effectively as possible. That's the essence of the entire Raptor program. The industry has tried for 60 years to make full-flow staged combustion work. For 60 years it has failed. SpaceX hasn't discovered any new physics. They just applied physics more consistently than any other company before them. And that's exactly what unsettles the established competitors so much. There is no secret. There is no trick that only SpaceX knows. The patents are public, the principles are known, the materials are commercially available. The Raptor 3 is not a better engine. It's a completely different understanding of how to build an engine. And that's the real revolution. And anyone who has seen our video about Leap 71 knows that the next revolution is already on the horizon. A huge thank you goes to today's video sponsor, Nuki. The link is in the description below. With the code MARSHRONIKEN, you get 15 off the Smart Lock Pro and Ultra. My name is Serwan, and that was Mars Chronican. Thank you for tuning in. Per aspera ad astra.